Okay, so this is going over the numerical solution to the Navier Stokes, again with an example. So basically the idea is here is the Navier Stokes on top. So this Navier Stokes equation basically tells how the velocity field changes with time. So the idea, see if I can get this to work. There we go. The idea is there's some kind of velocity field that's defined on this grid. It starts at time 0, and then after a time step, it's going to change, possibly in response to a force, into a new velocity grid. So the question is how to do this. So basically this Navier-Stokes equation gives a formula for how the u should change with time. So all of this together creates this change in u plus change in t, which then multiplied by t gives the difference in velocity. So taking the original velocity field and then adding that new velocity to it produces a new velocity field W. However, in general, W is not necessarily the U at the next time step. So this starts out with presumably this initial velocity field, goes to the next velocity field, and the question is how to do this. So in the case of the pipe, the velocity field is actually simple because the W actually is the new velocity. So for the pipe, all that it has to happen is this net force has to be computed. There's actually no pressure in it. The additional velocity per time step is just added to the velocity field at the beginning of the time step, and it just continues to accelerate downwards. So this is a trivial case for the pipe. However, for the water glass, that is not true. For the water glass, the velocity actually remains stagnant. That's because that V does not actually contribute. And in general, it should not be expected. In general, it should not be expected that W is actually going to equal U, because in most cases, W actually will have a non-zero divergence. So for the water glass, it was shown that what actually happens is the V's are cancelled by this gradient of pressure, and that basically stops all the motion. And in general, that's what happens. Motions that are illegal and try to put fluid into other fluid or going through walls are in general stopped by the gradient of the pressure, which is this term at the end. So this is what restores the fluid to being a fluid. And this is what generally has to be applied in order to convert W to U. So in general, this guy converts to U. So in this case, it just stopped it, but there's a more complicated scenario. So let's go over this. So start with a U at the start of the time step. So this is just a velocity field. We're going to apply a force. In this case, this is mostly a Gaussian force. There's some advection in here, but this is mostly a Gaussian force. Well, basically, there's just by a Gaussian, what I mean is basically there's just a force with a vector field off to the right and a little bit up, and it's applied in a Gaussian shape, so the force is strongest in the middle and less strong off to the side. And what this force does with this type of acceleration is this external force tries to move the fluid like this. So it tries to create this V, this change in velocity, on that section of the fluid. And so what happens is, if possible, this is what U would look like, because these were the original velocity field in basically blue and green, and this new attempt at velocity is in the red and dark red. So this would create this W if it was allowed to do this. However, W does not have non-zero divergence, so this light blue, dark blue light is a graph of what's going on with the divergence. So basically the fluid where it's dark, the fluid is basically trying to be compacted together, and here it's trying to spread out. So this is actually trying to create a hole in the fluid and then pack it in here. So this is not allowed. This type of velocity as a real velocity would actually cause the fluid to spread out here and disappear and increase in density here, and this is not allowed for a incompressible fluid. And the reason that is because this is coming entirely from the new V, the new attempt at change in velocity, because the divergence of B has this divergence, non-zero divergence, where it's increasing here, decreasing there. So this is what causes, it's precisely what causes the divergence of W. So there's a W again. So W is actually not what's going to come out, have to be put into the next time step. So the actual time step U is actually going to be the real U, which is graphed in blue and green plus this V violation. This is the part of V that does not actually contribute to a real velocity. So this is just looking at V violation itself. So these are all the extra velocities that are not going to be allowed into the final solution. So these are all attempts at motion that do not actually happen. And it's these attempts at motion, the violation, that actually have this divergence. These are precisely what is causing this divergence in the field. So what actually happens is, instead of having the fluid diverge, where fluid gets pulled out, gets less dense here and gets packed in here, what actually happens is a pressure builds up. So a high pressure region forms here and a low pressure region forms there. So the high pressure region basically pushes back against these velocities that are trying to go ahead and compact and spread out the fluid. And so this is what the negative gradient of pressure looks like. This is a negative gradient of pressure pushing back against the V's. So this pressure gradient develops to oppose these velocities that are trying to go ahead and violate the divergence of the fluid. And so this was W, which had the fluid spreading out. This is W plus the negative gradient of P, or W minus the gradient of P. So there's the W's with the gradient of P vectors going back. And that is the actual U at the next time step. So this is the real U at the next time step with the divergence of U in the background, and there was no longer any divergence. So basically it was the pressure field that killed off the incorrect velocities, and once the pressure field is taken into account, is set up properly to kill all the velocities that cause the divergence, then that pressure field can be the gradient of that pressure field can be effectively subtracted from the W, and that will give the U at the next time step. So summarize this briefly. So what actually is the U at the next time step? So what the U at the next time step is basically is actually just computed. It's basically just computing the pressure field. So we know that gradient dash W equals actually the divergence of W actually equals the divergence of V violation, which makes in turn means that it equals the divergence of the gradient of the pressure field plus some constants, which I think will delta T over rho. And then the other part of this is the boundary conditions. So Wx equals the constants and then the differential, the partial differential of P across that boundary. And this is x equals 0. So boundaries in general, and then the same thing goes basically for the y. Wy equals, again, the constants and the y equals 0. So these equations basically can be used to find the gradient of P. Gradient of P. And then after that, you just add the gradient of P to W. So basically, once the gradient of P is known, all that has to be done is it's basically added to W, and that will come up with the U for the next time step. So W vector plus, actually this is plus the negative of the gradient of P, or minus the gradient of P, equals basically the U at the next time step. So this is basically the procedure for evolving this field and numerically in order to find out how it behaves dynamically. So basically the simulation just repeats this process again and again and again to basically evolve the U. So the only part that remains to be seen is to discuss in more detail how to actually compute this part, which is actually the change in U per change in T, which gets the V and in turn the W.